Okay, so now we're diving back into the notes. Hopefully you watched the video about how to set up right triangles for trig substitutions. But back in the notes, so if you happen to remember the antiderivative of this integral, then you can just do it, right? So if you happen to remember that this is the inverse sine of x, then you're done. And so notice that we do have a difference of perfect squares showing up here, and so that's why this is under the heading of trig substitution. And notice, of course, the result does have a trig expression in it. So this relationship between square roots of sums or differences of perfect squares and trigonometry, of course, is there. But say you forget how to do that. How could you handle this problem? So let's notice that the denominator does contain this expression, the square root of 1 minus x squared. So let's use what we learned hopefully in the last video and try to figure out how we would label a right triangle so that the sides would match this difference of perfect squares. So remember that if we have subtraction, that means that we must have been solving for the hypotenuse in Pythagorean theorem, right? So if I was looking at Pythagorean theorem, it's a sum. The only way to get subtraction is if I were subtracting over and solving for one of the sides, right? Something like if I was solving for a, let's say. So a would be the square root of c squared minus b squared. So the point is that this 1 must be my hypotenuse squared. So my hypotenuse I'm going to label with a 1. And then my two sides are either going to be x or the square root of 1 minus x squared. And how I choose them, right, if I want to choose it x here and the square root here, that's fine. Or I can switch them, and that choice as to whether I want to switch them or not is really just going to come down to which trig ratio I'd like to work with, right? So it says now, so we drew our right triangle, we labeled all three sides, then we want to write the substitution using an appropriate trig ratio. So which ratio uses and makes easy to solve for x, right? So I want to use the opposite side and the hypotenuse side. I want to avoid this adjacent side, right? So this is my opposite and this is my hypotenuse. And so that's going to be sine, right? Sine of theta is equal to the opposite over the hypotenuse. So sine of theta is equal to the opposite over the hypotenuse. So sine is just x. So that's our substitution. And so anytime we have a substitution, we need to then take the derivative with respect to x. So the derivative of sine is going to be cosine and then d theta. Okay, so far we're really just doing what we did in the last video, but now we want to use this substitution to actually integrate this expression, right? So what I want to notice here is this dx, this is going to be really crucial to use here, right? So the classic mistake is for students to just write d theta here, but this dx, of course, is equal to cosine of theta d theta, right? And then we have this part of the integrand, which we need to replace, and this has expressions with x's in it, right? So one way to approach this problem would be to just brute force directly substitute, right? So I would be left with 1 over the square root of 1 minus, and instead of writing x, I'm going to write sine of theta and squared. And then my dx, which I already have here about rewrite, is cosine of theta d theta. Okay, so this would be a perfectly fine approach to how to start this substitution. And then I have this kind of mess down here in the denominator, but I just expand it out. So this is going to be 1 minus sine squared times cosine. And now we really need a trig identity. There's a trig identity, one of the Pythagorean identities, in fact, that says that, so it says that sine squared plus cosine squared equals 1. And so if I solve for, this should feel really familiar, all the Pythagorean theorem stuff we've just been doing, it's of course related. If I solve for cosine squared, I see that in fact 1 minus, let's highlight this, right? So we have that cosine squared theta is equal to 1 minus sine squared of theta, right? So I could, instead of writing 1 minus sine squared, I could write cosine squared. So this would be the square root of cosine squared. And of course, the square root of the square root and the square cancel. And so we're just left with 1 over cosine times cosine. But of course, that cancels also. So we've got all sorts of things canceling here. I'll use different colors. Now I've got cosine canceling with cosine. And after all is said and done, I'm really just left with the integral of, there's nothing left, just a 1. So I've got 1 d theta. And so how do I take the antiderivative of the number, the constant 1 with respect to theta? Well, the antiderivative is just going to be theta plus the constant, right? And so that's great. That's my answer, but that's in terms of theta. So as usual, once you've done a substitution, you have to back substitute and figure out what it is back in terms of x. So for this, I go back to my original substitution, right? If sine of theta is equal to x, how do I solve for theta, right? How do I, so let's change colors yet again. Why not? How about purple? So if sine of theta is equal to x, how do we get theta by itself? Well, we take the inverse sine of both sides of the equation, right? And so theta, I did not mean to cancel out the theta. I was trying to cancel out just the theta, the sign there. Inverse sine of theta is just theta. Theta is the inverse sine of x. And so our answer is the inverse sine of x plus c. So this is how we would integrate this expression without having memorized it. Okay, so I want to point out one little thing, and that is that we actually could have avoided all of this stuff and this substitution right here, because we have a right triangle and we want to take full advantage of this right triangle. So if I were actually doing this substitution from scratch again, so hold on, my computer's not happy. All right, here we go. So if I wanted to start this all over again, I still have to let dx equal cosine theta d theta, that's for sure. But is there any more efficient way I could have dealt with this square root of 1 minus x squared? In other words, did I really have to just use the x was equal to sine and then this Pythagorean identity and then cancel and all that? And the answer is no, because the whole reason we knew this was going to be a trig substitution problem is we saw this difference of perfect squares. And the difference of perfect squares is showing up as one of my legs. This is my adjacent side. So I'm really looking for an expression that is 1, my hypotenuse, over my adjacent side. Isn't there a ratio that is equal to, so 1 over the square root of 1 minus x squared, that is the hypotenuse over the adjacent side, right? So which ratio is hypotenuse over the adjacent side? That's just secant theta. So 1 over 1 minus x squared is secant theta, and then my dx is cosine theta d theta. And so in one step, the reciprocals cancel out, and I'm back up to here, that I'm integrating 1 d theta. And so the result follows. Okay, and we'll continue more of this in another video.